In this work, we introduce a unified reinforcement learning and optimal control-based approach for dynamic, terrain-aware, quadrupedal locomotion. We use the ANYmal quadruped to design, train, and evaluate our control framework, and further transfer it to ANYmal. We are able to do this transfer without retraining any of our RL policies, despite the fact that ANYmal is different compared to ANYmal in terms of mass and size. As part of our framework, we introduce 3 RL policies. A first-step planning policy, which, given terrain and robot state information, generates desired feed positions and forwards it to a whole body motion controller. A domain adaptive tracking policy, which generates corrective feed-forward torques in order to aid whole body motion tracking. And finally, an emergency recovery controller, which generates low-level joint position commands for quick responses to external perturbations. We use the elevation map local to the robot's base frame as a form of extraceptive feedback. However, instead of including it directly in the observation space of each of the RL policies, we train a denoising convolutional autoencoder so as to represent the elevation map in the form of a reduced dimensional embedded vector. This embedded representation of the elevation map, along with the robot states, becomes the observation space for each of our RL policies. Furthermore, since we use a physics simulator to train these policies, it becomes necessary to accurately model the dynamics of the system, making it easier to perform a sim-to-real transfer. In this regard, we introduce an actuator network as an approximation of the complex actuation dynamics of the physical system to generate an effective joint torque for joint position, velocity, and feed-forward torque commands.